Swayam Prabha. Digital India. Educated India.
Okay, so let me have your attention. Please take notes. Okay, and of course I want you to go back and also look at Presley. Okay, I am doing the same thing that Presley is doing, but I am trying to emphasize certain things that he is not emphasizing, and also gives a different perspective to things, slightly different perspective, but it's essentially the same thing. And the idea is that I want to do something that's complementary in certain cases to what is given in the book, so that you get better understanding. You put both views together, you get a better wholesome view. Okay, so you see, so let us continue with our discussion. See, what we are trying to understand is this business of signed curvature and signed normal. Okay, which are kind of which are geometrically kind of defined. All right, so I told you that there is the way to understand the sign curvature is that the sign is essentially coming from the so-called turning angle. The turning angle is the angle that the unit tangent vector makes with some fixed direction. Okay, and if that so if the, for example, if the unit tangent vector is turning anti-clockwise, okay, then this angle is increasing. Okay, and then the rate of the change of this angle is positive, and in fact the rate of change of this angle is the sign curvature. And why it is signed is because if this unit tangent vector is going to turn in the clockwise sense, then you see the turning angle is going to decrease. So the rate of change of the turning angle is going to be negative, and that is actually the negativeness of the sign curvature. Okay, so curvature as it is, if you think of it as only unsigned curvature, it has no sign, but the sign has to come in because you want to write out the you want a uniform way of writing all the equations. Okay, and the curvature vector is supposed to be along the acceleration. It should be the acceleration vector, but the problem is with direction. Depending on how the curve is being traversed, okay, either your sign normal will point towards the center of curvature or away from the center of curvature, and then the issue is that if it is pointing away from the center of curvature, then you want to put a minus sign. Okay, so that you want you want the acceleration always to be in the direction of the geometric normal. Okay, which if you want from physics, if you are looking at a uniform circular motion in positive sense, okay, then you have this acceleration vector pointing towards the center of curvature, which is the center of the circle. Okay, so but I told you the big deal is to understand that this business of bringing a turning angle into the picture gives you the sign curvature. So I told you last time, what I told you last time was, the idea is, what is it that you're trying to do? You're looking at the tangent vector and you want to record the change of its direction. So you take the angle made by the tangent vector with a fixed direction, let's say x-axis, positive x-axis if you want. And mind you, we are always, whenever we do these kind of calculations, we will always assume it's a unit speed curve. Okay, and therefore the parameterization is by arc length, and we will assume that it is parameterized by increasing arc length. Okay, so that is the convention. So you are taking a unit speed curve, therefore its tangent vector is unit vector, and then you want to measure the angle along with sine, the angle by which the tangent is turning, that's the turning angle. And the point is that the rate of change of this turning angle is actually the sine curvature, okay, and the sine is taken care of by, whether this turning angle is increasing or decreasing. If the turning angle is increasing, then its rate of change is positive and you get positive curvature. If the turning angle is decreasing, then the rate of change is negative, and therefore the sine curvature is negative, okay. So but what I did last class, that is what we saw last class, was that the critical thing is to define this turning angle, okay. And see, you want to define this turning angle, and of course defining it geometrically is very easy, but the point is, because it's an angle, usually the angle function is even discontinuous, okay, and it's also multiple valued. Therefore the problem is that, since it is an angle function, you have to be careful, and what I want is, I want the turning angle not only to be continuous, I want it to be differentiable, I want it to be continuously differentiable, and I want to say that derivative of the turning angle is actually the sine curvature. So for that I need a continuously differentiable turning angle, and the existence of that for any unit vector, a variable unit vector, is what we proved last time, okay. So let me so what I want to deduce now is that I want to really deduce these three facts. The first thing is that the sine curvature is the rate of change of the turning angle, okay. The second thing is, I want to tell you about these Frenet-Serret formulas, which are actually, it's a matrix differential equation, a system of first order linear differential equations, which completely governs the movement of a particle on the curve, which means essentially curves, the curve is determined by this matrix, okay, and the main character in that matrix is the sine curvature. So you see, that is another motivation for sine curvature being so important, okay. The third thing is, I want to also say this fact, which is, this is something that you should think is very, very obvious. If the curvature is constant for a curve, okay, or even if you take a piece of a curve, okay, then you should expect it to either be, part of a straight line or part of a circle, okay. And now you see, if you try to prove it with the general formula for curvature, it's somewhat difficult, okay, but with this turning angle it's very easy to prove. So this is also something that we will deduce, okay. So let me say the following thing. Recall that our how did we define the, so I have this curve gamma is equal to gamma of s, okay, and if you give me some point, then this is gamma dot of s, this is the tangent vector, and the norm gamma dot is always 1, so this is a unit speed curve, all right, and so this gamma dot is a unit vector, all right. And then I told you that the way the sine curvature is defined in a geometric sense is the following thing. So what you do is that analytically you rotate this tangent. Mind you, the tangent direction is always given to you, okay. That's because the direction in which the curve is being traversed, and here it is with respect to increasing arc length, okay. And then once you know the direction in which the curve is traversed, at every point the tangent direction, and this the tangent will be unit tangent, because this is unit speed curve, because the tangent is actually given by gamma dot, capital gamma dot, and that is the speed, the modulus of that is the speed, that has to be 1, okay. And of course this is thought of as speed, don't think of it as speed with respect to time. This is like speed with respect to arc length in that sense, okay. So gamma dot s, mind you, it's not it's not velocity. If you generally write small gamma of t, then gamma dot of t is velocity. It is d gamma by dt if you think of t as time. But here what you are doing is your parameter itself is s, okay. So this is also velocity in terms of s with respect to s, and its magnitude is speed in terms of s. So you must always remember that the parameter is arc length, okay. That's what you have to understand. Now as I the way we defined the sine curvature geometrically was the following. So we took this unit tangent vector, okay, and then we rotated it 90 degrees in the anticlockwise sense, and this was the unit normal vector. Okay, and then so I'm putting n hat sub capital S. Okay, and this capital S is the sign normal. Okay, don't confuse capital S with small s, which is the arc length. Okay, so I'll put it as, let me just put it as capital S and then put a small s also here. Okay, and how did you get this n hat s? This is the sign normal. You take the tangent and rotate it by 90 degrees anticlockwise. Okay, now what is the adjustment we made? See, in order to make sure that the acceleration vector always points geometrically towards the center of curvature, you have to write it like this. You have to write gamma double dot of s. Okay, this is the geometric acceleration. This should be in the direction of the geometric normal. Geometric normal is from the point on the curve towards the center of curvature at that point. And how is that written? It is written as ks ns hat. This is how we write it. And see, the point is, why did we write it like this? See, this is because, you see, if your sign normal is pointing in the direction of the geometric normal, then this ks becomes positive. It is to be adjusted to be positive. And if this sign normal is pointing away from the geometric normal, opposite in direction to the geometric normal, then this ks will become negative. And that's why we have put this sign to the curvature. Okay, that's how this sign curvature was defined. But now you see, what I want you to understand is that from this, you can get what this, you can show that this ks is actually nothing but d phi by ds. So, see, look at gamma dot s. This is a unit vector. This is a C1 unit vector. Remember, gamma is C2. Okay, it's a second continuously differentiable, so its derivative is first continuously differentiable. Okay, and what did we prove last time? For a first continuously differentiable unit vector, you can define a turning angle. Okay, that's what we proved last time. So, by what we did earlier, that is last time, you have there exists phi equal to phi of s, a turning angle for gamma dot of s. Okay, so that is a turning angle. And what is the definition of turning angle? You using that turning angle, you can call it as, you know, cos of that, sine of that. Okay, so remember, what was this turning angle business? If you had a unit vector, okay, and it parameterized by, let us say, t, okay, then the unit vector is given by components ft gt, okay, and then unit vector says that f squared plus g squared is always 1. Okay, what we showed is that you can write theta equal to theta of t. Okay, so that you can write ft is cos theta t and gt is sin theta t, the standard parameterization of the circle. This is all geometrically evident. What is not evident is how to get that theta to be first continuously differentiable and how to define the theta without a picture. Okay, and so we did all that and we proved that there is such a theta. I mean, the theta that you see geometrically is also can be captured analytically. Okay, and it was theta dot, there is a relationship between theta dot and f and g and their derivatives. Okay, and integrating that, you get theta. So you get theta as an analytic expression. Okay, so if you so if I just recall for a moment, so let me just tell you, if you had started with, you know, this ft gt as a unit vector and theta t is this angle, the obvious angle, then you see you would like to write ft is cos theta t, gt is sin theta t, which is correct. But then the point is that if you calculate, if you think, the problem is whether this theta t is actually continuously differentiable. Okay, because always let me again first trying to show an angle is continuous or that is differentiable or it is continuous differentiable is always a mess, because naively an angle function is always multiple valued, it is always discontinuous. Okay, so there is always a problem. So whenever you are dealing with an angle, you have to be very careful. Okay, The fact is, if you assume this, what happens is differentiation tells you that if theta were differentiable, then theta dot is given by this formula. Now what you do is that you turn the roles and say, let us define theta by this formula, by integrating this formula. Okay, and then after you have done that, then you have to show that this theta t will satisfy ft is equal to cos theta t, gt equal to sin theta t. That's what we did last time. Okay, so the point is, let me again tell you, is to show that that theta can be captured analytically, and that whatever that is analytically is also geometrically correct, and that theta, because you captured it analytically as an integral, it's continuously differentiable. That's the whole point. Okay, so now there is a turning angle. That means what? Therefore this implies that this gamma dot s can be written as cos phi s comma sin phi s. So this is the whole point. Okay, any unit vector can be written as cos of its turning angle, sin of its turning angle. That's all. Now you see, now calculate gamma double dot. Gamma double dot of s is, what is it going to be? It's going to be d by ds of gamma dot of s. So I have to differentiate this vector, but differentiation here means you differentiate every component. Okay, so it's component wise. So I differentiate, if I differentiate cos phi s, I'll get minus sin phi of s, and then this phi s has to be differentiated. I'll get d phi s by ds, and for the sin phi s, I'm going to get cos phi s. Okay, and then again I have to differentiate phi s. I'll get d phi s by ds. And you see, this d phi ds by ds is a constant. I can pull it out. So I'll get d phi s by ds times what I get is minus sin phi of s comma cos phi s. Okay, right? And now just think about it. See, if gamma dot is this vector, what is the analytic or geometric definition, if you want, of the unit sine normal? You have to rotate this vector by 90 degrees anticlockwise, and you have to get the sine normal. But if you rotate by 90 degrees anticlockwise, this is what you will get. So you see, this gamma dot s rotated by 90 degrees anticlockwise in the positive sense is going to be ns. So let me put n capital S of s. Okay, and I'm putting a cap just to tell you that it's a unit vector, and that is exactly this guy. This is what it is. If you rotate x comma y by 90 degrees anticlockwise, it will become minus y comma x. All right. So therefore, what are you getting? Therefore, this implies on the left side, you see, you are getting gamma double dot is equal to d phi s by ds times ns hat. Okay. Now compare this with the geometric definition of gamma double dot. Gamma double dot is actually ks ns hat. Okay, that's how we geometrically defined it. But what we are getting is now gamma double dot is d phi by ds ns hat. Therefore, this ks has to be just d phi by ds. Okay, so compare with our earlier definition. Gamma double dot is equal to, so I'll put an s there, d, and here also let me put an s. So d phi, here the earlier definition was ks ks of s ns hat of s. Okay, so the subscript capital S is for sine, the small s is for arc lengths. Please don't get confused. So you compare it with this, and then you see immediately that this guy is the same as this guy. So this implies that the sine curvature is actually d phi s by ds. So that is the whole point. The sine curvature is the rate of change of the turning angle. Okay, so that is the first thing that we. So now you see this sine curvature. You are able to see sine curvature now as an analytic expression. Mind you, this phi s is a turning angle that we got analytically. Of course, intuition is geometric, but you got phi s analytically. Okay, and you got that it is C1, and its derivative is your sine curvature. So you see, the sine curvature was just introduced to put a right sign so that your acceleration vector always correctly pointed towards the center of curvature. Okay, that was a physical or geometric thing, but now it is analytically giving you an expression. Okay, so that's what you have to understand. And the hero of the movement is this turning angle. Okay, that's what helps. Okay, now so this is one thing. Then the second thing is I want to tell you about the so-called Frenet-Serret relations. The Frenet-Serret relations, basically, I mean, this Frenet-Serret relations, what is the whole idea? See, the idea is, let me say at least twofold. One thing is you would like to make sense of the statement that, a curve is completely controlled by its curvature. Okay, that is one. I mean, if you know the curvature of a curve at every point, you should know it. Okay, that's one thing. The other thing is that if you think of it from a physical point of view, a curve is just trajectory of a point moving. After all, when you parameterize a curve, you think of the point moving on the curve with a certain velocity, and twisting and turning as per the curvature of the curve. So it is dynamics of a point moving on a curve, and usually these dynamics are given by equations of motion. All right. So usually you have a differential equation which should give these dynamics. Now the fact is that there are basically this is in 2 dimensions, so you should expect 2 differential equations. Okay, in each one in each component. Okay, so essentially you should be able to write differential equations. Okay, either one in each component, or one as a matrix differential equation 2 by 2 matrix differential equation, and that's exactly these Frenet-Serret relations. And the big deal is that these Frenet-Serret relations completely characterize the curve. Okay, so what are the Frenet-Serret relations? It's like this. So you see, as you take this curve gamma of S. Okay, see, at every point I have a moving frame which is called the Frenet-Serret frame. What is that? There is this gamma dot of S, which I will use a new notation. I will call it as T cap S. So this T cap is unit tangent. Okay, and then there is the there is a normal. So this is so this guy is the n s hat of S. This is the sine normal, and of course you have gotten this by going like this 90 degrees, okay, anticlockwise. So you should see that as this point gamma S. So let me remove the S there. So as this point gamma S moves, you see this orthonormal frame. Okay, this pair of mutually orthogonal unit vectors, that also moves. Okay, if you know the dynamics of that, okay, if you know how these t and n change, if you can record that, okay, then that should give you the equation of motion of the curve, of a particle on the curve, if you want. All right, and basically what is the equation of motion? Basically you have to write out the velocities. You have to write out the changes in the variable. So basically what I want to know is I want to record the change in the normal direction, the sine normal direction, and I want to record the change in the tangent direction. Okay, and what happens is, here's something beautiful you get T dot. So you see there's an extra dot there, that is actually the change in instantaneous change in T cap. Okay, this is the change in T cap. See, the curve is gotten, as the curve moves, this T and N is also moving, and I want to record the change of T and the change of N. That means I need their derivatives. So there is T cap, there is NS dot cap and the dot. Okay, so it's messy, but let me write it like that. This is what happens is that this is actually what you get is this skew symmetric matrix. You get this. These are the Frenet-Serret equations. Okay, if you want to write it as 2 first order equations, you write T cap dot is equal to Ks into n hat, and so n. So let me write ns here, and n is cap dot. So be very careful with the dot. It's minus Ks T cap. Okay. If you write it individually, it's like this. Okay, and basically this is a bunch of equations which is telling you how this frame, this moving frame consisting of T and N, how it's changing. Okay, and what is the curve physically? It's just a solution of this differential, this system of differential equations. Either you can see it as a system of differential equations, or you can think of it as a matrix differential equation. The point is that you have this beautiful skew symmetric matrix here, and the only thing that is occurring there is, you see, just the sign curvature. See, if you believe that the curve is going to be essentially controlled by this, then it's clear that this differential equation is controlled by this matrix, but the matrix itself is controlled by Ks. So more or less what you are able to see is that the curve is controlled by its sign curvature. Okay. Now there is a small hitch here. Okay. There are a couple of hitches. One thing is, we have to, these are all, we are making intuitive statements, but you have to make them very formal. That is also part of the game. There is another thing, where is this sign again coming in? See, if you are very loose, you will say the curve is controlled by its curvature. You will not worry about sign. But why is this sign coming in? So the business is about this idea of when two curves are considered the same. Okay, so I want you to absorb this idea. You see, if you take a circle, okay, and then you take any other circle, these two are essentially the same. Okay, if they have the same radius, you can superimpose one on the other. Okay, and then therefore what you would like to say is that to say something is any two objects, for example curves are the same, you would like to say you can superimpose one on the other. All right, and this business of taking something and then superimposing it on the other, in R2 this can be done by just using a rotation and a translation, and these are called rigid motions. Even in R3 also it can be done just by using rotations and translations. Okay, so you can easily see that if I take a curve, I translate it, okay, and then that is, translation is just moving a fixed distance along a fixed direction, and then or if I rotate it either clockwise or anti-clockwise, the curvature at every point is not going to change. Okay, so this curvature as it is a translation or rotation invariant, you can see that. Okay, so when you say curve, you should identify all the curves which can be superimposed on each other, and these are all the curves which can be moved to one another by rigid motions, which come as composition of translations and rotations. Okay, for all these curves, you see the curvature should be the same. Okay, because the curvature is just the shape of the curve, and if you can superimpose one curve on the other, the shape is literally the same. But where is the sign coming in? Because the sign is coming in the following way. You see, if you put an orientation to the curve, then there's going to be a problem. If I take two circles and don't care about the orientation, if two circles have the same radii, I can literally translate them. I can translate the center of one to the other and they will be superimposed. But imagine that I have two circles, one going in the clockwise sense and the other going in the anti-clockwise sense. Okay, suppose you keep also the sense in which you are traversing it, okay, and you try to superimpose, then you will be in trouble. What will happen is you would have superimposed the circles, no doubt, but you see the points will be traveling in the opposite sense. And what is it that distinguishes? It is the sign curvature that distinguishes. Because of the change in the sense, you see the sign has changed. Therefore, what this should tell you is that I cannot take a clockwise movement on a circle and move it by a rigid motion to a clockwise, anti-clockwise movement on the same circle. I cannot do it. What has to be done? I have to actually use a reflection. It's only a reflection that will change the orientation. Okay, and reflections are not rigid motions as it is. Okay, so the moral of the story is that you see the sign curvature takes care of this extra thing, that two curves, you consider them to be the same. When you say that they have to be superimposable by rigid motion, I also want this orientation also to be preserved. Okay, And in fact, what the rigid motion will do is it will preserve the orientation. It is a property of the rigid motion. Okay, and it's because of that that if I take a circle, a particle moving in a circle with anti-clockwise sense and another particle moving on the same circle with clockwise sense, I cannot move one to the other by a rigid motion. Okay, the rigid motion will preserve sense. Okay, I cannot move from anti-clockwise to clockwise. I cannot do that. Okay, I have to use a reflection. So therefore moral of the story is the sign curvature is important because it also keeps the orientation in mind. Okay, and with this what I want to say is that you can make a statement like this. On one side you can have all possible curves. Okay, if you want you want a standard parameterization, take unit speed parameterization and fix them on an interval. Okay, and you also make sure that any two curves which are which can be moved by rigid motion, you identify them. Okay, and you take this set. See, when one curve is identified with another by a rigid motion, this is an equivalence. Okay, if I can take every curve is equivalent to itself because I can use the identity transformation. And if I can move one curve to another curve by rigid motion, every rigid motion has an inverse which is also a rigid motion. Okay, therefore I can bring back the second curve to the first curve. Okay, so this relation is symmetric. Okay, and if one curve can be moved by rigid motion to another curve, and then this second curve can be moved by rigid motion to the third, to yet another curve, then I can move the first to the third by the composition of two rigid motions, because the composition of rigid motions is also a rigid motion. Therefore you see, this business of one curve being rigid motion equivalent to another is an equivalence relation, and what you are doing is you are taking the set of equivalence classes of curves, and the statement is that this set of equivalence classes is in bijection with all sign curvature functions. Okay, so this is the correct statement that the curvature determines the curve. Okay, so this has to be done properly. All right, now what I am going to do is I am going to do later this in the 3-dimensional case, which as a special case will also include the 2-dimensional case. So I will come to it later, but I want you to understand again the importance of the sign curvature. It is the sign curvature controls the curve up to rigid motion, and more importantly it controls the curve with orientation. That is the power of the sign in the sign curvature. Okay, so that is to tell you something about the importance of this, but deriving this is a very easy thing. See, we have already written something here. We already have this. You see, we have this equation tells you, mind you, this is now this is just t cap dot. This is what it is, because you see t cap is gamma dot. T cap, the unit tangent, t cap of s is defined to be capital gamma dot of s. Okay, therefore t cap dot of s, mind you, every dot is d by ds, so it will be capital gamma double dot of s. Okay, but that is equal to ks ns, and therefore you see this is automatic. So this we already have. What we need to show is this. Okay, and where did that come from? For this second Frenet-Serret equation, again you use the important the feature of the turning angle. Okay, so this comes from the turning angle, so that's again the power of the turning angle. So what happens is, you see, you know that gamma dot s is that phi of s is the turning angle. Okay, so gamma dot s is cos phi of s comma sine of phi of s. Okay, now calculate gamma double dot of s. Okay, and what you get is, you do d by ds, then of course you will get ks into ns hat. Okay, mind you, this is t cap dot. All right, now what you do is, but what is ns hat? see this, the point is this ns hat is, you see, the unit vector, I mean this gamma dot turned by 90 degrees in the anticlockwise sense. So this ns hat is going to be minus sine phi s and cos phi s. Okay, this is what it is, all right, by definition. And I want ns hat because that is, this is the second, this is what I want to calculate. So ns hat dot, I want the dot of that, so I have to do d by ds. So if I do d by ds and differentiate it, what will I get? I'll get minus cos phi s, derivative of phi s will give me a d phi s by ds by chain rule, okay, and then I'll get minus sine phi s, and I'll get d phi s by ds. This is what I'll get. But watch what this is, I can take the minus d phi s by ds out, and I'll get a cos phi s comma sine phi s, okay. But this cos phi s sine phi s is exactly gamma dot, which is, mind you, t cap. So this is and this guy is the sine curvature. So you get this is equal to minus ks t cap. So you get this second Frenet-Serret relation. And mind you, you are getting this, you know, this minus k. You have to watch that. You see the minus sign. Yeah, that's exactly the point. They both are the same. So that's correct. I mean, it's correct to think that, you know, if you believe it from a differential equations point of view, it's correct to think that a first order differential system of differential equations, if you give me one set of conditions, namely initial conditions, then the solution is unique, okay. And if you think of it from a differential equations point of view, it's correct to say that the Frenet-Serret differential equations, if you fix initial conditions, then the solution curve of that is unique. But how do you fix initial conditions? You have to give me a point, and you have to give me the Frenet-Serret frame at that point, okay, because these are derivatives of the Frenet-Serret frame. Basically that means you want a curve passing through a point, and such that the Frenet-Serret frame at that point is the frame that you have prescribed, which is going to be a pair of mutually orthogonal unit vectors, okay, and that has to be unique. And the point is, if I take this whole curve and make a translation and a rotation, the sine curvature is not going to change, and you still get, for the new curve, you get the same differential equation. Therefore, when you want to say the differential equation gives you the original curve, you either fix a point and give the Frenet-Serret frame at that point, or you say that any two solutions, they will differ by a rigid motion, okay, and that is a classification theorem, all right. So that's, so you have also a differential equations point of view, you also have a physical point of view, but it is essentially one and the same, okay. In fact, you know, these are all nice ways of saying that, you know, the curve is controlled by its curvature, you know, which is a very loose statement. If you want to say it, you know, physically, you are saying the equations of motion control the trajectory of a particle. That's a physical way of saying it. Mathematically, what is the way of saying it? If you give me a first order system of differential equations with the initial condition, there is a unique solution. The solution is exactly the curve. So both ways of thinking are correct, okay. So this is the Frenet-Serret equations, okay. Then I want to come to, you know, so I will just make this, I'll just make this statement. We will do this in more generality, so I'm not going to get into this now. I will just say theorem. This theorem is, you know, classification of curves of, and here I will say that there is a bijection, natural bijection. On the other side, you will have let me say never vanishing so I just want to say so let me not say that, I'll just say so let me just say curvature functions that is you know, kappa from A comma B to R, okay, and the map is, so there are, so I should tell you what this is all about. Just in words, the map is you just send any curve gamma or its equivalence class, you just send it to the signed curvature. Okay, this is the map. So basically what I am trying to say is that, you know, if you give me any curvature function, there is a curve for which that is a curvature function. Okay, that is the first statement. So that is the surjectivity. And what is the injectivity? The injectivity is if you give me two curves with the same curvature function, then they must be equivalent by a rigid motion. So this is, you know, equivalence by a rigid motion. What does this mean? What do I mean by putting a slash here and putting a tilde? Actually, I am taking quotient by an equivalence relation, which means I am taking the set of equivalence classes. So basically what is there on this side can also be written as the set of rigid motion equivalence classes of curves, of unit speed curves. And how do you, if you have an equivalence relation on a set, it partitions the set into equivalence classes, and the quotient by the equivalence relation is just the set of equivalence classes. Okay, and that's what I mean by putting this slash and putting a tilde below that. Okay, so this set is also the set of rigid motion equivalence classes of unit speed curves on AB. Okay, that's what it is. Okay, and basically this is a classification theorem. But what I'm going to do is that I'm going to prove this more generally for space curves, and there what is going to happen is that, you know, I'm going to have for the space curve you have one more curvature, which is the torsion. So I'll get a general theorem which along these lines. In the plane case, I am saying that the, you know, the curve up to rigid motion is controlled by the sign curvature. In the space curve case, I will say that, you know, the curve up to rigid motion is going to be controlled by its curvature and torsion. Okay, and if you take that theorem and specialize it to the case of plane curves, you will get this theorem, and I am going to prove that later. So I am not going to prove this separately. Okay, but I just want you to understand that, you know, if you think of it just as a uniqueness of you know, differential equations, a uniqueness theorem of differential equations, or as a, you know, this philosophy that, you know, the trajectory is completely determined by the equations of motion, then it is kind of more or less the same. And you have to only remember that the equivalence you have to mod out by the equivalence, because you have to two curves which are rigid motions of each other, the curve which is sine curvature is not going to change. Okay, the rigid motion will also preserve the, not only the curvature but also the sine curvature. Okay, all right. So so this is the importance of that. But now I want to prove a, you know, rather again a rather silly sounding statement. Namely, suppose you have a curve. Okay, suppose its curvature is constant. Okay, then you should expect it to be either part of a straight line or a part of a circle. Okay, how will you prove this statement? Okay, now if phi of s is a turning angle, for gamma dot of s. Okay, so by the way, whenever I say turning angle, yeah, you have a question. I mean, I should say, sorry, I should have said, yes, thanks. So if a curve is part of a circle or a straight line, then its sine curvature is constant. I should not say 0. Sorry. So if a curve is part of a circle or a straight line, then its sine curvature is constant. Okay, I should, yeah. So if a curve is a part of a circle or a straight line, then its sine curvature is a constant, and I want to say that the converse is true. So we have a unit speed curve. You take a turning angle for that. Okay, and what does that mean? It means gamma dot of s is cos phi s comma sin phi s. Okay, what is the curvature is d phi by ds. Okay, curvature, the sine curvature we just saw is Ks of S is d phi of S by ds, okay, and this is given to be constant, okay. So let us take two cases when the constant is 0, that's easily dismissed, and then we will take the constant is not 0, okay. So suppose d phi of S by ds is equal to 0, okay, then if you integrate it you will get phi of S is equal to, so the integral d phi S by ds let me say S0 to S, then this should be equal to, on the left side I should put phi S minus phi of S0, okay, by the fundamental theorem of calculus, okay, and but you see this is 0, so basically I will get phi of S is equal to phi of S0, which is say phi naught, okay. Therefore what it means is that this should give you a straight line, basically because gamma dot S will become, cos phi naught sin phi naught, okay. So it means that the unit tangent vector is constant. That can happen only for a line, for a straight line. And how do you verify it? You actually write out what gamma is by again integrating once. So gamma S minus gamma S0 is going to be again by fundamental theorem of calculus integral from S0 to S gamma dot S ds, okay, and so it will be integral from S0 to S of this vector cos phi naught comma sin phi naught ds, and you are going to simply get S minus S0 into cos phi naught comma sin phi naught, okay, and this is gamma S minus gamma S0, and this is the equation of a straight line, okay. If you think about it, gamma S, capital gamma S is gamma S0 plus S minus S0 times cos phi naught comma sin phi naught. This is a straight line, okay. This is an oriented straight line. Basically if you draw a vector picture, basically you have let us say some point gamma S0, okay, this is the position vector, okay, and then gamma S is, you see, if this is gamma S, okay, then this vector is gamma S minus gamma S0, okay, and you are saying that gamma S minus gamma S0 is this, which is S minus S0 times this unit vector. So this is equal to S minus S0 times u cap, where u naught cap, where this u naught cap is this cos phi naught sin phi naught. So basically this direction gamma S minus gamma S0 is, the direction is constant, is the same direction as u naught cap, and then as S increases you are only going along the direction of u naught cap. So this is actually equation of this straight line, okay, with orientation given by increasing S. So if the curvature is 0, it's part of a straight line, okay, so you get that very easily. Then you can similarly see that if the curvature is constant, non-zero, then you will get a circle, and if that constant is going to be positive, it's going to be oriented circle with the orientation anticlockwise, and if the constant is negative, then you are going to get clockwise orientation, okay. So let's look at the other case. Suppose d phi S by ds is equal to constant, let me say is equal to k naught, and suppose it is positive, let us say, okay. Then what happens, you will get, if you integrate, you will get phi S minus phi of S0 is equal to integral from S0 to S d phi S by ds, and this is going to be k naught into S minus S0, okay. And now if you put it back into the, so you have to put it back in the equation for gamma dot, okay, and then integrate to get gamma, okay. So gamma dot of S is cos phi S, because phi S is a turning angle, and sin phi S. So you will get cos of phi S is going to be k naught into S minus S0 plus phi S0 comma sine k naught into s minus s naught plus p of s naught. Okay, and now you integrate this again, you will get gamma s minus gamma s naught is integral on the other on this side. You know what you are going to get is that when you integrate this with respect, I will get norm of gamma s minus gamma s naught, and if I take norm on the right side, I will get 1 by k naught. Okay, and mind you, k naught is positive, so I don't have to put a mod. And this is the equation of circle, center this, radius this. Okay, and you can also you can also draw a picture and see that this is exactly the this is exactly going around in the anticlockwise sense. Okay, so so therefore the moral of the story is that if the curvature is constant and it's positive, you get a circle in the anticlockwise sense, and if the curvature is 0, you get a straight line, part of a straight line. Okay, if the curvature is negative constant, then you get a clockwise oriented circle. So what I want to say is that I mean, all this should convince you that the turning angle is very important. Okay, and it gives you a key to doing all these things. All right, so we will continue in the next class. All right, so